Today we're going to talk about recursion. And recursion is one of those topics that always hurts the brains of students. Like it just feels like your brain is melting and coming out of your ears the first time they learn it. And it's hard. Like the only way really to understand recursion is to understand recursion. Like you just have to do it enough times and write enough code and get comfortable with it that it sort of becomes second nature to you. So let's start off on the server here with a little bit of recursive code. Let's see here. Okay, move main.cc to space. Okay, main.cc. Okay. So let's say I have a function. And I'm going to call the function, somebody give me a function name. Grundle. Okay. So a recursive function is a function that calls itself. How many times is this function going to call itself? What do you guys think? Infinite. Yeah. It's infinite. Eventually, it's actually probably going to Stack Overflow. It's unclear if it will. But yeah, this is an infinite loop. This is a while true loop with more steps. Okay. So what if I did something like this? What if I had a integer here, integer x equals 0, and const int max equals 100, and I said if x is greater than max, return. Is this code going to loop forever? It will. It will. So, okay. What if I did? What if I made max 10? Still gonna loop forever? Yeah, still forever. Okay, and hello world forever. Okay, what if I put x plus plus here? Is it gonna loop forever now? Yes, it is. No, it's not. Wait a second. X is a global, right? So the first time through, X is 0. We post increment it, so we do the check first, and then X increments to 1 afterwards. And then it's 2, then it's 10. So after 11 loops, it's 10. Then on the 12th time, it'll return. So I don't think it's 10, Tipton. I think we got an off by 1 error in here. See? Run it. Pipe through word count by line, 11 lines. Yeah, this is an off by 1 error. So if we did this, though, we pre-incremented it, then we get 10 of them. Okay. So off by 1 errors are one of the most pervasive problems that we have in computer science. They crop up everywhere. We could also get an off by 1 error if we did this. If we moved the if statement down. Now we've got 11 again, because we're printing before we check. You know what I mean? And so, if you did greater than or equal to, then it's going to be off by 1 the other way. Like it's one of those things where you really should start with thinking of max at like 2, and just run through it in your head. Okay, the first time through, we're going to pre-increment x. So x is 1. Is 1 greater than 2? No. Print hello world. We call ourselves again. We pre-increment up to 2. Is 2 greater than 2? No, it's not. So we print hello world. We'll print it again. We print it's 3, and then it returns. Okay, we're good. And so you have to be very careful with things like that, especially when you have a non-standard for loop. One of the reasons why I teach you guys the standard for int I equals 0, I is less than 10, I plus plus for loop to do 10 things is because there's no counting on your fingers and toes how many times the loop is going to run. It's just, it's going to be 10 times. You follow that pattern. You guys all remember this, right? For int I equals 0, I is less than blah, I plus plus, right? Whatever you put after this, like foo or whatever, will get called 10 times. Whatever number is there is how many times it runs. You don't have to think about it. That's why I teach that pattern. And there's other reasons as well. Okay, so what if we called ourselves twice? How many times is this going to print hello world? $22 times? 10 times? 20 times? 10 times. The reason for that is because all of the variables are actually sharing the same counter, right? So it doesn't matter how many times you call it. Every time you call it, it increments x one more time, and if it's over the max, it just doesn't do anything. All right. Neat. Okay. So there's a sort of formal way of talking about recursive functions. Every time you do a recursive function, actually, let me switch to the presentation on this. I already got all this set up already. I don't need to type it all from scratch. There's actually a little bit of CSI 26, a little bit of preview of next semester. So, recursion is when a function calls itself, and this is what we're talking about there. So, here is a tree print. Like this is a print. This is the recursive print function, in fact, that you have for the current homework assignment, or very close to it. So, will this code infinite loop, or will it successfully print all of the nodes in the tree? What do you guys think? Take a moment, look at it. Let me get my tablet. Okay, so every recursive function has to have two things. It has to have a base case that stops it from running forever, and it has to have an inductive step that moves it closer towards the goal. So this guy here is missing the base condition. There is no stopping. In fact, what happens is that when you call DFS, it calls DFS, which calls DFS, which calls DFS, and it just sits there, and it will loop forever between these two lines, forever, until it cycles. Okay, so this code is an infinite loop with basically a guaranteed crash associated with it for good measure. So it's going to it's like if you had a tree, like this, it's just going to go to the left, go to the left, go to the left. Eventually, it'll hit null. Then it will dereference the null pointer and probably segfault. Okay, it might not. The optimizer might stop it from segfaulting, so there's no guarantee that it will, but that's probably what will happen. Okay. What about now? You guys see the difference between these two? What is the difference between the two? I added a base case, right? So what do you think? Does this code look good? Are there any changes you would like to make to this code? Does it look correct to you? Looks good to you? What about stylistically? Is there anything stylistically you'd want to change? Some people might want to use null pointer here. That's about it I can think of. Null pointer is probably better than null, but either way, correctness wise, it'll work exactly the same. So yeah, this code here is actually correct. You could argue over null or not. It's actually not going to make too big a difference here, but you could definitely argue over it. Okay. So here's a meme. Exhibit meme is a recursive meme, and so we have a recursive meme about recursive memes. Yo, dog, I hear you hate recursion. So I recurse myself on top of myself so you can learn to recurse while I recurse. There you go. So here's the secret of success in recursion. You need these two things. You need the base condition that makes it stop so it doesn't run forever, and you must always move towards the goal. It's like in a football field, you got the end zone, right? And as long as every time you take a step, you're taking a step towards the end zone, and as long as the end zone ends the the motion, eventually all the motions that you take on the field will eventually terminate with you hitting the end zone and then finishing. Okay. There is, however, this thing called the recursion depth limit, which is how many times a function can call itself before you run out of stack space and you segfault. What happens whenever you have a function is you've got all the variables on that function on what's called the stack. So you might have x and y and z on a function, and you got this thing called the stack pointer right here. And x might be 10, and y might be 20, and z might be 30. And then you call the function again. What happens is the stack pointer moves down. It makes another set of x and y and z. These can have completely different values. You can have 42 and -6 and 20. And then if it calls itself again, the stack pointer moves down again. And eventually you run out of stack space. And you have your x, y, and z. And then you call it again, and it explodes. Okay? And that is called a stack overflow. Yep. And this is a lethal bug. There's really not a very good way of recovering from it. So if you recurse too many times, you can actually run out of stack space and stack overflow. And that is what the website was named after. If you've ever been to stackoverflow.com, which is a website of people asking technical questions and moderators deleting the questions for being stupid. So after you spend enough time with recursion, though, you sort of internalize these rules, okay? So you sort of learn to think about them at kind of a higher level. You become big-brained and stuff like that. When you're starting off, it's actually hard to like wrap your mind around all the recursion. So like this function here, it's so small. It's only 4 lines of code, and it actually has very complicated behavior. If you've got a binary search tree, BST, and you got like 40 here, and 30 here, and 20 here, and 25 here, and 35 here, and you run this code, let's do 60 up here. Okay. You run this code, what happens is when you start off, n is pointing to root, right? So you have root pointing at this guy. And so when you start off, n is pointing at root. Is n equal to null? No. So then we recurse down to the left. And so now that n's still there, but we've got a new n pointing at this guy. Is this guy equal to no? No. So we recurse down to the left. And so we have a new n. These guys are still there. They're still on the stack. Remember, the stack pointer moves down. All those variables are still there so that you can like come back to them later. But in the meantime, like you're down here right now, right? And so you recurse down to the left. Now this guy's left pointer is null. And so when you have a pointer to null, we check that it's equal to null and we return. Then we print 20. So the first thing that we've output is 20. And then we recurse to the right. So we now have a pointer to 25. 25 recurses to the left, which is null. It doesn't do anything. It then prints 25. It then recurses down to the right here, which is also null. It returns. And then it returns up to here, and then it returns up to here, and then it prints 30. And then it recurses down to the right, it goes down to here, recurses to the left, it's null, prints 35. Recurses to the right, it's null, returns, prints 40. Recurses to the right, recurses to the left, it's null, returns, prints 60. Recurses to the right, returns, and the function's over. So this will print all the elements in the tree in order. 4 lines of code, and that's a very complicated movement pattern, right? So the path that this thing took was like coming down this way, and then coming up this way, and down this way, and up this way, and this way, and coming up to here, and going down to here, and like that, and then back up to here, and then down here, and there, and back up like that. So that's a pretty complicated path, you know what I mean? And it did it all, like in 4 lines of code. And so with recursion, you can actually have very powerful functions. A lot of people say it's very beautiful. You can have a very beautiful function. Very few lines of code can actually do very complicated behavior. And you just need to think of it so that no matter what level you're at, the code works. So from root's perspective, let's say we're just taking it from root's perspective now and not recursing downwards with our level of analysis. From root's perspective, n is root. And then it's not null. And then we're going to say basically print everybody in my left subtree. That's what that means. Because DFS, depth first search, takes a pointer and it prints everybody in that tree. And so we're saying print everybody in my left subtree right here. That means print everybody in my left subtree. And when it's done, we know all of our left subtree is printed. And then it's just up to us to print our data, 40. And then we say, hey, print everybody in the right subtree. And it takes care of that for us. If we switch our level of analysis to 30, then the left call here is going to print the 20 and the 25. And the right call is going to print the 35. And we print the 30 in between. And you can see no matter what level of analysis you look at, this code is correct. Okay. And we have the inductive step is correct, and we have the base condition is correct. And as such, we have a very good, very powerful DFS algorithm. The only risk is that if the tree is too big, or especially if the tree is unbalanced, that's the real issue. If the tree is unbalanced, we might exceed our recursion depth limit and cycle. So, do you guys understand these two things? Base condition means this, right? And then the inductive step means you're always moving towards progress. Okay. All right. So you guys got to tell me, is this code good? Is this code bad? Will it end? Is this code going to end? If you pass in 2 here, it's supposed to print out hello 2 and hello 1 and then terminate. Does this code work? Will it end? It's an infinite loop. Why? How do you know it's an infinite loop? Is there any way of escaping this rather than just calling itself again, right? Yeah, no base case. There's no end zone. This code will run forever. Every time you call helloer, it calls helloer 100% of the time. This is an infinite loop. Okay. So, good. You guys all got that one. How about now? We've got an inductive step now, right? So if we pass in 2, then it's going to print out hello 2. It's going to print out hello 1, and then it'll print out hello 0, and then it'll print out hello -1, that'll print out hello -2, it'll print out hello -3. At least we're moving, we're going somewhere, but there's no destination. There's no place that'll stop our infinite loop. Still, icky code will be infinite. That's correct. Every time we call helloer, it calls helloer. There is no escape from this. There's no return or exit or anything like that that would allow us to escape. So sure, we're moving towards the end zone, but there is no end zone. So how about now? How does this look to you? Will it blend? Yeah, so we got an end zone now, right? So if we ever, get 1 or below, we return, which is wrong, by the way. This is actually, this is not good. Because if we got 1, it actually returns before it prints it, right? Do you guys see that? So this is actually wrong in both the base case and the inductive step. So the base case should be less than 1, but it's less than or equal to 1. So if you pass in 1, it just returns. So we got an off by 1 error here. And then, yeah, this does not actually move towards the end zone. Okay, how about now? How does this look to you? X never changes. War never changes. How about this code here? We good? We got an end zone. If we ever hit 0, it returns. It's going to print out hello 2. And then we got the post increment. I don't know if you guys saw that. The post increment. No, it does print what we want. If we pass in 2, it's going to print hello 2. And then the decrement takes place after the line of code runs. So the double minus after the X means run that line of code, and then after that line of code's done, then decrement X to be 1. Okay. If we put the minus before it, then it would print out hello 1 because it pre-decrements it. So there's pre-decrement and there's post-decrement. Looks pretty good to me. I don't know. It's better than before, at least. Yes, very good, Harrison. If X is negative, it goes infinite. Remember, about half of all integers are negative numbers. And so if you pass in -1, it's going to print out hello -1, hello -2, hello -3, hello -4. And it's just going to kind of run for a while. It's probably going to stack overflow and crash. If you had infinite stack space, then what would happen is it would hit negative integer eventually. And then probably underflow back up to maximum integer and then go all the way down to 0 and end after printing out 4.2 billion numbers. Probably not correct, right? Probably not the best thing. And it probably wouldn't do that anyway. It would probably segfault. It would probably run out of stack space and die well before it printed out 4.2 billion numbers recursively. Good. A lot of people forget that, Harrison. A lot of people forget that because for whatever reason, they just think of integers as being positive or zero. And the reality is like half of all integers are negative, and people just forget that all the time. Like in professional code, like if you just pass in a negative number, like they just don't think that negative numbers exist. I don't know what to tell you. You know, they don't use an unsigned. They just don't handle negative numbers a lot of times. So yeah, true story. How about now? Here's an interesting one. So let's say that you're 5 squares away from somebody, and you flip a coin. And if you get a heads, you walk towards them. If you get a tails, you walk away from them 1 step. And if it lands on its edge, you just stand there. Will this code end? Will it terminate? You're starting off, let's say, 5 squares away. If you get heads 5 times in a row, it's over. If you get heads 4 times, then tails, then heads twice more, you win. Will this code end? With good RNG? I don't know. You tell me. What is the assumptions you make in your analysis? Best case running time is pretty good, right? Best case running time is you flip heads every time and you walk towards them every time. So if you call random walk 10, then well, you walk towards them 10 times and you're done. You know? What about worst case? Worst case is when everything goes wrong for you. You know, the data is always in the last place you look, right? What is the worst case running time of this? What do you guys think? Yeah, if RNGesus hates you, you're gonna flip tails every time and just walk away from them and never come back, right? And so you have infinite running time. So this code cannot be proven to terminate. Okay, it might, but you can't prove it. So this would not pass muster for like anyone's like professional code. Okay, so who is here that hasn't been talking in a while? Pina. Okay. And Sam. Okay, so you guys can answer the next one. I'm missing one of my slides. Dang it. Okay, well, Pina and Sam, let me just describe it to you in English. You flip a coin. If you get heads, you walk half the squares towards them, rounded up. And if you get tails, you walk 1 away. What do you think? Best case, worst case, expected case. What's your answer? Okay, anybody. You flip a coin, you get heads, you walk half the squares towards them, rounded up. So if you're 1 square away, you walk 1 towards them. If you're 5 away, you walk 3 towards them. If you get tails, you walk 1 away. So best case, worst case, average case. What do you think? Constant best case, infinite worst case. What about average case? On average, will it end? If half the time you walk, you're 100 miles away, you get a heads, you walk 50 miles towards, you get tails, you move 1 away, you're at 51. Get heads again, you're now 25 away. Get tails, you're 26 away. What do you think? It is more likely. In fact, probabilistically, you would expect for the algorithm to finish because you move forwards more than you move away. And since forwards and backwards has equal probability, it would probably end, but there's no guarantee. There's no guarantee. You just might get tails every time. That's the problem with randomness, right? Can't guarantee anything. Okay, cool. So what about the Fibonacci sequence? So we pass in the index of the Fibonacci sequence. So the first index is in the Fibonacci sequence is defined to be 1. The second index is defined to be 1 also. Then everybody after that is recursively defined. And whenever you have a recursive definition, you can have a recursive algorithm to solve it. every Fibonacci number is defined as the sum of the two previous Fibonacci numbers. Well, what are those Fibonacci numbers? Well, those are the sum of their two previous ones. And so every Fibonacci number can be defined recursively like this. Every number is equal to the sum of the two previous numbers in the sequence. So for example, 8 is the sum of 3 plus 5, 13 is the sum of 5 plus 8. Does this code end for all possible inputs? What do you guys think? No, it doesn't. What numbers did we forget about again? Negatives. Very good, Jonathan. Yeah, we forgot negatives again, right? Oops. Should have made that an unsigned integer. Or we could just make it less than or equal to. That's perfectly acceptable too. They're not supposed to pass in a negative number. We could feasibly die, if they pass in a negative index, because it doesn't make sense for there to be a negative index in the Fibonacci sequence. But this would work fine. Now here's a question. What is the big O running time of this algorithm? If you wanted to calculate, the 10th element, the 5th element with Mia Jovovich, if you wanted to calculate the 10th element, order n squared. Interesting take. So like if we wanted to calculate, like, let's say this guy here, index 0, 1, 2, 3, 4, 5. Okay. So if we wanted to calculate the Fibonacci of 5, we have to calculate the Fibonacci of 4 plus the Fibonacci of 3. Okay. The Fibonacci of 4 is calculated by computing the Fibonacci of 3. Oops, we're duplicating work, aren't we? And the Fibonacci of 2. Fibonacci of 3 is computed as the Fibonacci of 2 plus the Fibonacci of 1, which is going to return. Fibonacci of 2 is defined as the Fibonacci of 1 plus the Fibonacci of 0. Fibonacci of 2, oops, we're reduplicating work again. It's Fibonacci of 1 plus the Fibonacci of 0. Fibonacci of 3 is defined as the Fibonacci, I'm going to put the 1 on the left-hand side here, just so that I have room to write. And the Fibonacci of 2, once again, is recomputed as the Fibonacci of 1 plus the Fibonacci of 0. Now, if I were to add just one more number, and I want to compute this one, index 6 instead, what I would have to do, Fibonacci of 6, was compute the Fibonacci of 5, which is all that work, and then the Fibonacci of 4, which is all that work. So it's almost like every one number bigger, we do twice as much work. Every time we do one more number in the Fibonacci sequence, our total running time doubles. So we go from a running time of 1 to 2 to 4, simplifying very roughly and crudely, 8, 16, 32, 64, 128, 256, 512. This is not n squared. N squared looks like this. 1, 4, 9, 16, 25, 36. This is way worse. 1024, sorry. This is not n squared. This is the bad outcome. Okay? Order n squared is not that bad. This is something called polynomial time. And it's not great. If you're using n squared to compute the Fibonacci sequence, that's not great. You're not doing a good job. You can compute the Fibonacci sequence in order n time. You can. You just do it poorly. It's not anything crazy. This is called polynomial time, and polynomial time is aight. It's okay. It's acceptable. What this is, every time you go one step further, you double the work. This is called exponential time. And this is the bad outcome. All right? You don't want to see this as the result of your algorithmic analysis. Okay? If you wanted to compute the Fibonacci of 100, you're talking about roughly 2 to the 100th power operations. Which is a big number. It's a really big number. It's an unimaginably big number. When you should be doing 100 calculations. It's a really big difference between exponential time and polynomial time. It's a massive difference. And of course, we can do this whole thing and just order in time if we do it with a for loop. So go for loops. Yay. Better than recursion in this case. And there's ways you can accelerate the recursion so that it gets order in performance as well. Yeah. So this is exponential running time, and it is bad. You do not want to see this. And unfortunately, a lot of algorithms are what are called MP. So polynomial time, we say is, where's my mouse? We call it P for short. Non-polynomial, we call it NP. And you don't want, ideally, we live in, castles and fight dragons or something. But, in reality, a lot of games and things like that, like if you try to like analyze Othello or something like that, like you'll end up having like a non-polynomial result because there's like an exponential number of moves you can make, and life just kind of sucks. And so a lot of things in real life are exponential. And so when we solve them, we have to solve them in approximate ways. We try to come up with algorithms that'll kind of find an answer that's pretty good, but not necessarily the best. Like if you are like my old professor who worked at TC, who worked for Intel, I think. A lot of what he did was like chip optimization. So there's like an exponential number of ways you can put all billion logic gates on a chip. It's like 2 to the billionth. It's like an unimaginably massive number. Like forget about it. You can't try every combination to see which one is best. Like it's just unimaginably big. And so what he would do is his code would just try different things and try this and try that and try, there's a Boolean algebra thing we can do here to eliminate that. That's cool. And basically it kind of runs for a long time, but it's not like heat death of the universe long. It's not like, the sun will engulf the sun. The sun will engulf the earth by the time we finish Fibonacci 100. It's not like that, but it's also not perfect. It doesn't necessarily give you the optimal best ever result. It'll just give you a result that's pretty good. So exponential is bad. Okay. It's do what you can to have your program not be exponential. It is death on wheels. And your code could work. Like this code works. This code works fine for small numbers. Like what is 2 to the 6th power? It's nothing. Whatever. You do it in a heartbeat. By the time you get up to 100 numbers, forget about it. Okay, so basically for recursion, in short, what you're looking for is the two things that I talked about. You want the base condition to be a nice big end zone, right? Like the problem we had with the previous one here was the end zone was very narrow. So if anybody started in the negative zone, it would just return the Fibonacci. Like the Fibonacci of negative 1 is the Fibonacci of negative 2 plus the Fibonacci of negative 3. Well, what's the Fibonacci of negative 2? Well, that's the Fibonacci of negative 3 plus the Fibonacci of negative 4. And it just runs forever. So we had a very narrow end zone here. So when you think about this, the thing that stops it, make a nice big one like this. Like have a nice large end zone that'll stop anything, in its tracks. And then also make sure that you always progress towards the end zone. So if I left off in negative 1 here, it would loop forever. If I left off the negative 2 here, it would loop forever. So always make sure that you're taking steps towards the end zone with your recursive functions, and you're going to do good. Okay, so this is a little preview of Seaside 26. Next semester, what we're going to do in lab time today is we are going to write, and by we, I mean you, are going to write, you're going to write a recursive add function. So the main.cc, let's see, under Minkrelli's account. Some BSD. That's it. Okay. So we run it, and it's going to add up all the elements in a tree. So given a binary search tree that is full of integers, I want you to add up all of the elements in the tree. Okay. So I've got some demo code for you guys. The demo code is in /public/bsd.cc. And so you can go ahead and copy this code. And you can see right here, we've got a function called recursive sum. And what you're going to want to do, it's going to be very similar to recursive print. That's why I put it right above recursive print. It's going to be very similar, but instead of counting anything, what you're going to be doing is like returning values, and you have to like add values together and things like that. So like add all the people in my left subtree, then add my value, then add all the people in the right subtree. Make sure you got your base case, make sure you got your inductive step, and you're going to have half an hour to do this. Okay. So I'm going to put the link up on Canvas, and I mean you should see it anyway, but go ahead and make a copy of this one here on Canvas. Sorry, Discord. There's the code. You guys got half an hour. Begin. So the no discard attribute will help you guys in writing this. And what this means is it will warn if you call a function that returns a value and that value is important, it will warn if you don't actually catch that value. Like a getter, like pretty much all of your getters should be marked as no discard, because there's absolutely no reason for you to call get size. And it's like, here you go, here's the size of the tree, and then you do this, right? Where it calls the function and then there's no variable catching the value, right? It's like you throw a head of lettuce to a dog and it just goes on the ground. No, like normally dogs will catch anything you throw them for food. You throw them a hot dog and grab it out of the air. But vegetables, they just doesn't register. Just right. That's what we're doing here with get size. We're calling get size. We're not catching it. We need to say something like this, like integer x equals get size. Then the warning goes away. And so if you ever call a getter, you're not actually doing anything with the value that was gotten. It's probably wrong, right? And so it's a good idea to throw no discard. This is a compiler attribute. It's square bracket, no discard. Put that in front of your recursive sum function here. And then if you ever call it and you don't actually get the sum out of it, you're doing something wrong. Okay? Just as a pro tip for you guys. And it's kind of generally a good thing to know too, right? And you can just slap it on front of like every getter you have. Like, I don't know, get data, no discard. Get left, no discard. Get right, no discard. Okay? Like anytime you have a getter, it's probably a good idea to mark it as no discard, because why would you call it if you don't want the value? You know what I mean? So it's just a warning. It's not a compiler error. Sometimes people mark things as no discard when they should not be no discard, like error codes and things like that. Because sometimes I don't care about the error code. Like let's say I tell my computer to play a sound, and maybe the speakers aren't on and it returns an error, but I don't care. You know what I mean? Like I don't care if it worked or if it didn't work. Like I don't care. But they're like, no, you need to know this. You have to check the error message. I'm like, I don't care, dude. If it failed, I don't care. Like the sound didn't work. Who cares? They have their speakers off. They're not hearing anything anyway. And so sometimes I would care, but like a lot of times I just don't care. And they're like, no, it's no discard. You can't ignore it. And that kind of bugs me when they return things that honestly should be ignorable. But this will help you in writing your code. Okay, pausing the recording again. All right, let's come back, everyone. So the problem is not catching the recursive sum. So it's going to be very careful. You got to be very careful not to just discard the return value. So we want to have a variable here called int sum equals 0, and we want to add up our value. We don't want to see out anything. We're going to add up this value and this value and this value. So we'd say, for example, sum plus equals recursive print. Sum plus equals get data. Get rid of that end line there. Sum plus equals recursive print to the right, and return the sum. And that's it. That's the code. So basically, what you're saying here, if I could put this in plain English, and if we have an empty tree, it should return 0. Dim is null. Adding up all the values in an empty tree is 0. Right? So what we want is just to add up everybody to the left, add our value, our number to it, and then add up everybody to right, and return that value. And if I do this, then I'm summing up all of the values at my node and below. So that is a recursive print function. All right, let me switch over to a third recording for today. We're going to talk about the spaceship operator real fast.